Hi everyone, this is Dr. J, and in this video we're going to talk briefly about MASW, or the multi-channel analysis of shear waves method for seismic site characterization. Now the motivation for this is that in terms of looking at buildings or roads, bridges, landfills, you name it, one of the most important geotechnical properties that there are for site characterization is what's called VS30. And this is the shear wave velocity in the upper 30 meters of the subsurface. Now, why is VS30 so important? The reason has to do with the fact that the shear wave velocity is related to the shear stiffness of materials. So shear stiffness has to do with the strength of the subsurface materials, whether that's bedrock or soil, the strength of those materials to withstand shear waves passing through them, or shear shaking, shear type shaking. Now this is very important in areas that have earthquake hazard because earthquakes generate strong shear wave motion, and in fact they generate stronger shear wave motion than compressional wave motion, at least in terms of body waves. Anyways, shear wave velocity in the upper 30 meters is a widely used parameter for site characterization, and it's used in characterizing site response for simplified earthquake-resistant design. It's used in building codes, provides unambiguous definitions of site classes and site coefficients for site-dependent response spectra. So VS30 is a very important parameter, and again, it's just simply related to the shear strength of the soil and or bedrock of the upper 30 most meters. So it's used a lot in geotechnical work. Anytime you want to know, can I build my whatever on this site, one of the first things you're going to do is to try to measure VS30. Now one of the problems, or not problems, but one of the complications is that VS30 is shear waves. And as you've already seen in seismic refraction, we're using P waves. We're using first arrivals, which are P waves. Shear waves travel slower than P waves, and so determining the seismic shear wave velocities is not so easy. And so what has been done in the last 2 decades is to use this MASW method or other methods that are similar, but basically all these types of methods, they use Rayleigh waves, which are actually surface waves. And Rayleigh waves are useful because they are an approximation for shear waves. So actually your book says that Rayleigh waves typically have about 5% slower velocity than shear waves. So once you measure the Rayleigh wave speed, all you need to do is to multiply that by a conversion factor to get the shear wave speed. The other thing about Rayleigh waves is that they're surface waves. So they're only sampling, a particular depth. They're traveling along the surface. The longer the wavelength of the Rayleigh wave, the deeper it's going to penetrate. So a longer wavelength wave is going to actually penetrate down deeper into the subsurface. And so this is a very nice way of kind of getting at a particular depth. Remember, VS30 is the top 30 meters. So we want to be able to distinguish the seismic shear wave velocity in the top 30 meters from what's deeper than that. And we can do that using Rayleigh waves by using specified frequencies. So the MASW method, I'm not going to go into a lot of details about the theory, but basically what it does is it uses what's called dispersion analysis. And this is basically taking our seismic traces that we've already looked at and converting that to a phase velocity versus frequency. So different frequencies are like different wavelengths of the seismic waves. And then the phase velocity is how fast that particular frequency is traveling through the subsurface. And this curve that you can kind of see here, which starts out mostly flat and then changes to mostly vertical, this is what's called a dispersion curve. And by tracing out this curve, the software is able to essentially invert that for a series of seismic velocities with depth. So given a particular set of seismic waveforms or seismic acquisitions, you estimate the dispersion curve from those acquisitions, from these dispersion images, and then the software can invert that into a velocity model, essentially with an arbitrary number of layers, but usually you specify like 5 layers or something like that. And you can see here that the depth is going down in this case to about 15 meters. But that's going to be dependent on frequency, and so by changing the frequency you can go down to as deep as 30 meters. Now you will need to have a very strong source to get those longer wavelengths that are going to penetrate deeper. So that's one point that is important, is that you need long wavelength excitations from your source. So you'll need very strong sources, very strong hammer swings in our case, or other larger sources to generate those low frequency waves. And then once you have this velocity with depth measurement from the software, then you can simply average that to get the average shear wave speed in the top 30 meters. Okay, so that's a basic overview, very, very high level of how MASW works. I'm going to point you to this website to learn more, as well as a couple other places, and we'll have your reading just a few pages in the textbook to cover that as well.